Hello everyone and welcome to Data Platform Summit 2020. My name is Velida. I'm a software engineer and Microsoft Data Platform MVP working and living in Auckland, New Zealand, and I'm super excited to be talking to you all today about graph databases in Azure Cosmos DB. Now, if I was giving this talk in person, I'd usually start the session by asking attendees around the room what their experiences are with Azure Cosmos DB, have they ever used the Graph API, have they even heard of graph databases, etc. But since I can't see you all in person today, I'm just going to set expectations for this session by saying that this is just designed to introduce you all to what graph databases are and how we can build them using Azure Cosmos DB. So it doesn't matter if you've played around with Cosmos DB before, or you've dabbled a little bit in graph databases, or if you're a complete beginner. This session is just a real basic introductory session just to get you all excited about graph databases and building them using Azure Cosmos DB. But before we continue, a bit more about me before we start. I'm a software engineer based here in Auckland, New Zealand. I've lived in New Zealand now for almost 10 years, even though I've managed to keep a hold on to my accent. As you may have guessed already, I'm originally from the UK. I'm also a Microsoft Data Platform MVP, primarily focused on Azure Cosmos DB, but I also like to dabble a little bit in the integration space, so I work with Azure Functions quite extensively at work. I use Event Hubs quite a bit, Azure Service Bus, Azure Storage. I also like to dabble around in ML.NET, which is a really cool C# machine learning library, for those of you who haven't heard it. I like to blog on platforms such as Medium and DevTO, just sharing my passion for technology with anyone and everyone who wants to hear it. But anyway, what we're going to be talking about today, just to give you a little bit of an overview of what we'll be discussing. First off, I'll talk about graph databases, what they are and where we would use them. This will include going through the very basics, so what are nodes, what are edges, and how we can use properties and labels to describe our nodes and relationships and edges. I'll then talk about why we would use Azure Cosmos DB for our graph databases, what the benefit of using Azure Cosmos DB for our graph database is, and what they are, and what type of applications we can build using graph databases in Azure Cosmos DB. I'll then move on to how we can model our data for use inside graphs for Cosmos DB by taking you through a step-by-step process for modeling our graph data to ensure that when we're modeling our graph data, we model it appropriately that suits the needs of our application. I'll then take you through a quick demo to show you how you can actually set up a Cosmos DB account with the Gremlin API enabled, followed by creating a graph inside that account, adding some data to that graph along with some basic querying. Finally, after the demo, I'll give you some resources that you can take away from this session if you want to dive a little bit deeper on graph databases in Azure Cosmos DB, followed by a Q&A session. So if you do have any questions, please feel free to ask away. With that, let's dive into the session. So let's start off by talking about what graph databases are. So in the wild, data is naturally connected, and essentially graph databases are designed to treat the relationships and connections between our data as if they are as important as the data itself. Now, highly connected data can be a challenge to manage under traditional modeling techniques. Other databases compute relationships when we query the data through join operations. But in graph databases, relationships are perpetually stored within the database, which allows for quick retrieval of data that lives inside our graph database. But let's break this down a little further and actually go through what makes up a graph database. Let's start with vertices or nodes. Now, nodes are essentially discrete entities within our graphs. These can be a person, such as myself, or a place, such as my house. They are the fundamental units in our graphs, and they can hold any number of attributes called properties, which are just key value pairs, and we'll talk about that in a little bit later. And these are joined together by relationships or edges, and essentially they describe the relationship between our nodes. So taking this very basic example, I live at my house. Relationships provide a named and directive connection between two entities. So using this example, I live at my house, essentially is saying that I have a directed connection between me and my house. Now, relationships always have directions, a type of relationships, and a node from which the relationship starts, in this case me, and an end node for which the relationship ends, which is my house. And then there's something called properties. Now, properties express information about our vertices and edges. We can have any number of properties in either our vertices or edges, and we can use these to filter objects when running our queries. So in this basic example, I've got some properties for me as a vertex. So I have my name, my age, my occupation, location, and interests. So when we're querying my vertices, I can actually use this to describe and filter this when I'm performing my queries. And then finally, we have labels. We can tag our nodes with labels to represent the different roles that our nodes have within our domain. We can also use labels to attach metadata to certain nodes. When we use labels, we can use them to group nodes within a set. So when we perform queries, we can perform them within the set of labels rather than having to perform them within the entire graph. So you can imagine as we scale our graph up and up and up, using sets can be a really good way of making sure that our queries are efficient when we're actually querying data within our graph. So in this example here, we can group multiple vertices by using the user label that are associated with this web application. A real basic example, but that's how we can use labels to put those people entities within a user label within a user set. So let's take a look at this example. So here I've got my entities for me as a person and a couple of friends of mine, Alex and Mike. We can see a relationship between me and as my entity and my house. So I live at home, which is a relationship which is a basic relationship I described earlier. We can also see a relationship. So me, I work as a software engineer. I play rugby. I've got a relationship between an entity Mike who uses a phone which runs Windows OS, and basically what I'm trying to showcase here is that by using graph databases, we can actually build out relationships between data that may not appear connected, but may not be obviously connected together, but we can actually use graph databases to connect and express these relationships between these entities quite effectively and efficiently. So let's talk about why we would use graph databases and when we would actually need to use graph databases. So we would opt for graph databases if the data in our applications would have the following characteristics. If our entities are highly connected through descriptive relationships, we can benefit from using graph databases in this scenario with the knowledge that the relationships between our entities are persisted in storage. If there are cyclical or relationships between our entities or our entities are self-referenced, we can use graph databases. This pattern is often a challenge when using relational or document databases. So this is where graph databases have the edge when our data has these relationships or has this characteristic. If there are dynamically evolving relationships between our entities, graph databases are a huge advantage for this. This pattern is especially applicable to hierarchical or tree-structured data with many levels. And if there are many-to-many relationships between our entities, graph databases are also really a really good choice for this when our data has many-to-many relationships. And if there are read and write requirements on both entities and relationships, we would opt for graph databases if our data happen to have this requirement as well. So where would we use graph databases? You might be thinking, okay, this is all starting to make sense, but where would we actually use graph databases? And what type of applications can we build using graph databases? Well, First example, we could use them in IoT applications. So in this scenario, we could model the connection between our IoT devices and understand how they connect between each other and how they affect each other within a network. We could use them in recommendation engines. So we could combine information about our products, about our users, and how they interact with those products to build recommendations for our customers that are personalized to them. We can also use them within social networking applications, combining data about our users to connect people with similar interests to each other or create personalized experience for that user based on their activity and how they use that application. And then finally, we could also use them in geospatial applications. So we have a bunch of users, we can find locations of interest to particular users based on where they're currently located, or perhaps we're building an application that needs to determine the shortest route between locations, and that's also another fantastic use case for using graph databases. So there are several options to choose from when picking a graph database provider within the graph database ecosystem. So some popular examples include Neo4j, IBM Graph, OrientDB, Titan, Kaylee, Arango. But with lots of options to choose from, why would we choose Azure Cosmos DB for our graph database? Okay. For those of you that don't know, Azure Cosmos DB is a globally distributed, massively scalable, multi-model database service that offers global distribution, elastic scaling of both storage and throughput, automatic indexing, and tunable consistency levels. We can build a variety of different databases using table storage, columnar storage, document storage, and of course graph storage. For graph databases, it provides support for the Apache Tinkerpop standard. Now in the wild, graphs need to scale beyond a single server. Azure Cosmos DB is really ideal for this because it supports horizontal scaling and can have unlimited size in terms of both storage and throughput. And we can distribute our data using graph partitioning, which will handle our distribution and partitioning needs as our graph needs to scale. With Cosmos DB, we can replicate our graphs to any Azure region worldwide. Cosmos DB is a foundational service in Azure, meaning that no matter which Azure region throughout the world you want to use, you can provision a Cosmos DB account in that region. So with this replication, we can replicate to any Azure region worldwide while ensuring minimal read and write latency. We also have the benefit of having automatic regional failover capability for our graph databases to ensure that our applications stay up in the case of regional outage. Remember that Cosmos DB is a fully managed graph database service. So we don't need to manage any virtual machines, we don't need to update any runtime software ourselves, manage sharding or replication. All of that is managed for us. So all we need to do is just focus on developing our applications and developing our graph databases as we need to. And any management stuff is managed for us. Now by default, Azure Cosmos DB will automatically index all the properties within our nodes and edges in our graph and doesn't expect or require any schema or creation of any secondary indexes or indices. It also provides compatibility with the Apache Tinkerpop standard, which has a great ecosystem of apps and libraries that can be integrated with the Gremlin API. We can store vertices and edges and then query them using the Gremlin syntax. Now, the Gremlin syntax is an imperative functional query language that provides a rich interface to implement common graph queries and algorithms that we can use with our graph data, and that's what I'll be showing you in our demo later on. Cosmos DB also enables us to perform real-time queries and traversals without the need to specify any schema hints, secondary indexes, or any views like that. So it's a really fantastic service to build graph databases in the cloud. Now just a quick mention of the Apache Tinkerpop standard. Apache Tinkerpop is a graph computing framework for both graph databases and graph analytic systems. It's open source and vendor agnostic. It's not just limited to Cosmos DB. And whenever our data is enabled, Tinkerpop enabled, we as users are able to model our data as a graph and then analyze that graph using the Gremlin graph traversal language. And I've attached, I've put a link there to the documentation. So if you want to check out more about Apache Tinkerpop, that's a fantastic resource to go a little bit deeper into the Apache Tinkerpop framework. All right, now let's discuss how we can actually model our data for use in graph databases. So when we approach data modeling in graphs, this is just one way we could approach it. Now, this will obviously change depending on the type of applications that we're developing, and this is also based on the assumption that we know our data and we have a good idea of how we're going to query our data. So with that in mind, I've outlined 4 simple steps for graph modeling that I'm going to talk through now, starting with modeling our vertices and then modeling the properties. Then we would model the direction of our relationships, followed by making sure that we label our relationships correctly so that we can properly express them. All right, let's start with modeling our vertices and properties. Now, the first step we would take in modeling our data would be to map each entity that we've identified into a vertex. There are a couple of ways, a couple of approaches that we can take when doing this. The first one that I've represented here is by using a vertex-based properties. So in this example, we have 3 separate vertices, one for me, one for my job, and another for my country of birth, along with a couple of edges to describe its properties. Now, this approach can be great for reducing redundancy within our data, but since we're introducing more vertex objects here, it does increase the complexity of our graph, which can have an effect on latency, the type of queries we can perform, and the computation cost. So, an alternative to this approach is to instead embed our properties within the vertex. So in this example, instead of having my occupation and nationality as separate vertices, I've now embedded them as properties within my vertex, as a person. So as you can see, I've got my vertex of will, I've got a label of user, and then instead of having separate vertices for both my nationality and occupation, I've just embedded them as properties within my person vertex. This is really great for helping reduce the complexity of our model and will also lead to simpler querying when we want to retrieve this data. Let's talk about modeling our relationships with edge directions next. So after we've modeled our vertices, the edges can be added to note the relationships between our different vertices. Now remember, when we define our relationship, we're essentially connecting two nodes, and it allows us to find related nodes of data. So within any relationship, we'll have a source node and a target node, which shows the direction of that data. So in this example here, I've got 2 people nodes, so one for me and one for my friend Mike. And here we're actually showing the direction of their relationship, so Will knows Mike. So here I am the source node and my friend Mike is the target node. And we're defining a direction from my source node to Mike as a target node. Now we can, once we know our relationship between our entities, we can actually label them. Now when we label our relationships, we should be as descriptive as possible. We should try to use non-generic terms to label a relationship and make sure that the label of the source vertex is associated with the target vertex with the correct label. The more specific we can be when doing this, the better, as this will have an impact on query costs. So if we look at our example on the left, I've got a bunch of people vertices. So I've got myself, my friend Alex, Samuel, and Michael. And I've labeled my relationships as knows, with that label knows. And my vertex is just whoever the name is and person. This is too generic, so from this we might be able to deduce, that me as a vertex, I know someone called Alex, I know someone called Samuel, I know someone called Michael, but we're not really being descriptive enough when labeling our relationships. So while we might be able to make an inference on how I know these people, or at least know that I know these people, we don't know the exact nature of this relationship. So when we take our example to the right, we can see that I've got a node for myself, Will, as an engineer. I have a friend called Alex, who is my manager, and we can note that relationship by saying is managed by, or add that as a label. Then I've got a vertex for my nephew Samuel, and I can label that relationship as is family. And then I've got my best friend Michael as a vertex, and I can label that relationship is friends with. So here we're being far more descriptive of our relationships, and then when it comes time to querying our data, this can really help our queries be more efficient, because now we have more descriptive relationships to work with. Right, now let's move on to data partitioning in Cosmos DB graphs. And let's discuss how partitioning actually works when it comes to using graph databases inside of Azure Cosmos DB. Now both our vertices and edges will be stored as JSON documents. Vertices require a partition key, and this key will determine in which partition the vertex will be stored through a simple hashing algorithm. The partition key property is named when it's defined, when we create a new container, and I'll show you how easy that is to set up when we go through our demo. Edges are stored with a source vertex, so in other words, for each vertex, its partition key defines where they are stored along with its outgoing edges, and this is an optimization to avoid any cross-partition queries. All edges contain references to the vertices that they point to, so they're all stored with the partition keys and IDs of the vertices that they're actually pointing to, and again I'll demonstrate how this works in our demo. And then when we perform graph queries, we need to specify a partition key. And this is done to take full advantage of horizontal partitioning in Azure Cosmos DB. So when we perform our queries, the partition key should be specified when a single vertex is selected, whenever it's possible. So some best practices when using partition graphs: always specify the partition key value when querying a vertex. Getting a vertex from a known partition is a way to really achieve that high performance, and then all subsequent operations will be scoped to that partition, since our edges contain a reference ID and partition key to the target vertices when we perform our queries. Use the outgoing direction when querying edges whenever it's possible. So as I mentioned earlier, edges are stored with their source vertices in the outgoing directions, so the chances of resorting to cross-partition queries are minimized when data and queries are designed with this pattern in mind. When you're choosing a partition key, choose a partition key that will evenly distribute data across partitions. And this decision heavily depends on the data model of your solution. So think of a property that within your data that will help achieve that even distribution across partitions when you're choosing a partition key value. And then optimize queries to obtain data within the boundaries of a partition. So an optimal partitioning strategy would be aligned to the querying patterns that you're going to make within your applications. And just a general rule of thumb, queries that obtain data from a single partition provide the best possible performance. Alright, enough talking, let's kick into our demo. So in this demo, what I'm going to be doing is I'm going to start off by creating a graph database in Azure by creating a Cosmos DB account with the Gremlin API enabled. Then once that's been created, I'll create a graph inside our account and show you how we can use the Gremlin syntax to insert items into our graph. Then once we have some data inside our graph, I'll show you how we can then use the Gremlin syntax to query our data inside our graph database. Let's get into it. Okay, so here we are in the Azure portal, and we're going to go ahead and create our graph database in Cosmos DB. So to do that, I'm just going to click Create a Resource. And here we can see that Azure Cosmos DB is quite popular, so we can just go ahead and click that, or if we can't find it, we can just type Cosmos DB in the search bar here and click Create to get started creating our Cosmos DB graph database. So when we create our Cosmos DB account, we need to assign it a user group, so I'm just going to use an existing one. Then we need to give it a name, and remember this name needs to be unique across Azure, so I'm just going to call it Velida Cosmos Graph DB. Oh, that's not available. I'll just say Velida Graph DB then. Cool, it likes that. Now we need to choose our API. Now remember, Azure Cosmos DB is a multi-model database service. So we have 5 different models to choose from, but when we create a Cosmos DB account, we can only select a single API to use for that account. And luckily in this case, we're just going to be using this Gremlin Graph API, so we can select that. But it's just a thing to note that if you're working with graph data in one aspect of your application and document data in another, you'd need to provision 2 separate Cosmos DB accounts. But that's not an issue for this, so we'll just select Gremlin and carry on. Then we need to select a location. I'm currently in New Zealand. So I'm going to pick a data center close to me, Australia East, which I believe is in Sydney. Then we need to choose a capacity mode. Now, this is a pretty new feature, but essentially we can create serverless graph databases in the cloud. That's a lot of buzzwords, a lot of cool in one sentence, but essentially what that means is the difference between provisioned throughput and serverless throughput. When we use provisioned throughput, we're essentially provisioning throughput at a constant rate, and there are different ways that you can do that. But in a serverless situation, we would only pay for throughput when we use it. And just for this example, I'm going to keep on with our provision throughput mode. But what I'll do is I'll set it really low so I don't get charged too much. There's also a free tier that you can provision with Azure Cosmos DB. If you're doing a bit of prototyping, you can use a free tier. You're limited to 1 account per subscription. I'm actually going to do that for this one. Hopefully I've got a free one left. We can choose an account type. There's no real difference here. It's just a different UI experience. I'm going to use production so it feels like we're using the real thing. We can also enable geo-redundancy and multi-region rights, which is a little overkill for this demo, so I'll ignore that. And then we can also enable availability zones to help improve the availability and resiliency of our application, but I don't need to do that for this tutorial, so I'm just going to click Review and Create. And what I will actually do, I'll actually take you through, we can also enable networking as well. So say if you're wanting to connect your Cosmos DB account through a private endpoint, you can set that up here. You can configure any firewall rules, create or connect your Cosmos DB account to a virtual network inside of Azure. You can also define a backup policy, whether you want it to be periodic or continuous. This is a private preview at the moment, but essentially you can enable continuous backup of your data, which is really beneficial. You can also bring your own customer managed keys for encryption, and then you can also apply some tags to it. Say if you're managing multiple resources and you want to tag them just for management purposes, you can do that on creation as well. But we don't need to do any of that. I just thought that'd be interesting to show you. So once we click Review and Create, it's just going to do a bit of validation to make sure everything's okay. It looks like everything's good. We've got a name, we've got our API, or Gremlin API enabled. That's all we really need for this demo. So I'm going to hit Create. And I'm going to let that cook for an estimated 5 minutes of time, and then once that's done, we'll come back and continue the rest of the demo. Cool, now through the power of video editing, just a couple of seconds later, we've got our graph database ready and raring to go. Once you've created your Cosmos DB account, this is the control plane. So here we can set up some data replication, define the consistency level that we want to set at our account, do some backup and restoring, just configure that, enable any firewall or virtual network protections, manage our keys. We can get some keys, the keys to control our account and perform operations to our account here. We can do some basic monitoring, get some metrics, set up some logs, and also raise a support request if we need to. But never mind that for now. What we're going to be doing is we're just going to create our first graph. So what I'm going to do is just click this Add Graph button. And here we're going to add our first graph. Now for this demo, what we're going to be doing is we're going to be building a very basic graph for a hypothetical hobby social networking application. So essentially what we're going to be doing is we're going to be adding vertices for users or for people, and we're just going to be giving them a few properties as saying, and essentially assigning them hobbies that they're interested in and that they take part in for the purposes of a hypothetical scenario for connecting users with similar hobbies together. So in order to do that, we need to create our graph. And here in Cosmos DB, what we're going to do is we're just going to give our database a name. And then within this database, we're going to create a graph. What we can do when we're actually creating databases and graphs, we can provision the throughput either at the database level or at the graph level. Now, if we provision it at the database level, all our graphs within that database will share the throughput amongst them. But if we define it at the graph level, that graph that we provision throughput for will only have, that graph will only use the throughput allocated to it. And this allows us to be more granular in the way that we control our throughput. So say if we have one graph with lots of read and write operations on it, we can provide that with much more throughput than say another graph which might not have so many operations being performed onto it. So I'm going to use autoscale with a maximum level of 4000. For those of you that don't know, this is a new feature in Cosmos DB. Essentially, when you provision throughput, you can either provision it at a manual level or an autoscale level. And with autoscale, it gives us a little bit more flexibility. So essentially, it will scale between 10% of this maximum RU right up to the maximum, depending on the level of traffic that we experience. So I'm just going to keep it on the minimum for now. And then we need to give our graph an ID, or essentially give it a name. And for this purpose, I'm just going to call it people graph. And then we need to give it a petition key, and this will be used to automatically petition data amongst multiple servers that we use for scalability. And for this graph, I'm just going to use this hobby petition key. So we will just essentially, when we perform our queries and when we insert data, it will be petitioned on this hobby property. Sweet, everything looks good. So let's click OK. And through the power of video editing, our graph database and graph have been set up. Fantastic. Alright, cool. Now that we've got our graph set up, let's build our hobby scenario that I referred to earlier. And for this, we're going to add some vertices that represent people within our graph. And all these people vertices will have properties for their first name, last name, age, hobby, where they're from, and where they live. So we're just going to do the first one very slowly step by step, just so we can understand and get familiar with the gremlin syntax. So with the gremlin syntax, all we need to do is just type G, and then we'll have access to all the interfaces and all the graph operations that we can perform with the gremlin language. So what I'm going to do is I'm going to add my first vertices. So with this add v command, what I'm going to do is just for real estate, zoom in a little bit. Is that going to be, I'll collapse that tree for now and expand it if we have to. Anyway, alright, so let's add our first person and give them some properties. So we just use this property method. And remember that properties are just key value pairs. So I'm just going to give first name of Will. I'm going to be adding myself, add another property for my last name. Velida, add another property for my age, which is on 29. Add another property for user ID. Add a final property. Well, add a property for hobby. And let's give you kayaking, because I actually like to go kayaking in New Zealand. And give a final, give a from property of UK. Then a final property, this will be my final property, of lives in NZ. Brilliant. Okay, I seem to have lost the execute button, so I'll just zoom back out a little bit. Alright, awesome. So essentially here what we're doing, we're just adding a new vertice for person, giving it a property, giving it some properties for first name, last name, age, user ID, hobby, from, and lives. So we just click execute. And there is our first node or vertice. Isn't that amazing? So there we go. We've got a label of person, which we've added when we've added our vertice. And here are our properties: first name, last name, age, user ID, hobby, from, and lives. So now that we have a basic understanding, I'm just going to add some more vertices. Just copy and paste. So I've got one for Gemma. She likes hiking, she's from New Zealand and lives in New Zealand. Add Mike as well. And then also add Sloan. So there should have all my vertices that I need. So now what we can do is we can actually add some edges that will represent the relationship between our vertices within our application. So let's start off by describing a relationship between Will and Gemma, and let's say that Will knows Gemma. So let's go through this step by step. So again, use G to access gremlin, and then for vertices, we're going to go has label person. So we're just getting the label of our vertices. And then we're saying if it has a first name of Will, what we want to do is add an edge using this add e command of knows. And then we want to, so essentially in this first part we're defining our source vertice, and now we want to, we've got this directional edge relationship of knows, and then we need to define our destination node. So again, we will just use this command to, and then within this to method, we'll define our vertice, which has a label person and has a property of first name Gemma. Make sure I put all my parameters. Yep, cool, awesome. So once we execute that, we have defined our edge. So now we've got this ID, so we've got this in vertice, and that will be the ID of our will vertice here. And we've got an out vertice, which will be the ID for our out vertice. So let me add a few more relationships. We'll do slow nose will, and we'll do Mike knows Gemma as well. Execute that. Fantastic. Cool, awesome. So now that we've added a few things, we can start running some simple queries. So let's run a query that will return all the people within our graph database that have kayaking as a hobby. So again, I want to use gremlin, access vertices, and then what we're going to say is for those vertices that have a label of person, we want to return all of them that has a hobby of kayaking. Let me execute that. And as you can see here, let me just zoom out a little bit. Come across here. We can see those return results have been returned to us as a graph. So there are 3 people within our hobby graph that were returned as results in our query. And what we can do is we can actually click on each node to see their properties. So let's have a look at this one. So this is Sloan Timms, has a hobby of kayaking, and she knows Will Velida. So he is our target for this node here, a source for this node here. So we can say this is our source node who knows Will. And then here's Gemma. And we can say that Will has a target relationship of knows with our Gemma node. So that's some fairly straightforward graph querying or gremlin queries that we can perform to actually insert some data and perform some very basic queries using the gremlin syntax language. Okay, so what I've done in the background is I've just added a few more vertices so we can actually have a play around with a few more queries that we can perform in gremlin. So essentially what we can do, if we wanted to count how many vertices that we had, we can just do a very simple gv dot count. Let me just zoom in. So essentially all I'm telling the gremlin engine here is to say, hey, get all the vertices and then just show me how many there are. So we execute that. Oh, I've got to enter the brackets. There we go, and I get a JSON response of 8. So I've got 8 vertices returned to me. I can see some query stats there. Okay, now let's play around with some filters. Now, in Gremlin, we can actually filter data using Gremlin's has and has label steps, and then combine them using some operators to build more complex features. So what we're going to do is I want to get all the users or all the people vertices that has a label of person, has an age less than, I'll say 30 this time. I tested this on 40 earlier, but let's have a look at 30, see how many vertices get returned to us. So we've got 2 vertices, and this is returned to us as a graph. So here we can see my will vertice with age at 29. You can see the relationships, And then we've also got another vertice here for Sloan, age of 21. Fantastic. Alright, let's move on to projection. Now we can project certain properties in the query results using the value step. So for this query, what we're going to do, I want to project all the vertices, all the people vertices, or person vertices, that have values of hobby. Make sure my syntax is right, and you execute that. And here we've got a JSON response of all the hobbies that exist within our graph projected to us. And that's pretty cool, pretty neat. Now, with these query operators, these could work in any type of databases, whether it's traditional SQL relational databases, whether it's document databases or graph databases. So let's do a bit of a deep dive. Let's explore some queries that we can use in graphs and where graphs are really, really performant. Now, graphs are fast and efficient for traversal operations when you need to navigate through to related edges and vertices. So what I've got is, I've got a vertices of Thomas. And what I want to do is I want to find out all the people that Thomas knows with a vertices that has a label of person. And essentially, what we're doing is we're using the out E step to find all the out edges from Thomas, and then traversing to all the in vertices from those edges using this in V step. So if I execute that, I've got a very simple graph, but what's happening is we've got a relationship here now with Thomas, who essentially knows Mary. And we've also got our Ben, who Thomas knows. So if we just come back here, so also Thomas knows Ben, and we've also got Mary, who Thomas knows as well. So it's a very simple query, and that's a very basic example, but here what we've done is we've found all of Thomas's friends. Now, using this in our hobby application, we could then use this relationship to suggest to Thomas certain hobbies that he could do with his friends due to the fact that they know each other. It's a very simple, but it's still very powerful way of building complex queries and being able to implement powerful graph traversal logic using the Gremlin syntax, which is really, really fantastic. So in this demo, what I've shown you is I've showed you how to provision a Cosmos DB account with the Gremlin API enabled. Remember, when you provision your Cosmos DB account, you can only provision one API at a time, and I've showed you how to do that for a graph database. Then I demonstrated how we can actually create graphs within our account, how simple that is to do via the portal. Remember that with Cosmos DB, you can actually do this through infrastructure as code tools such as PowerShell, the Azure command line interface, and even Terraform if you're a Terraform fan, but that's beyond the scope of this this demo. I just wanted to show you how simple it is to set up a graph database inside the portal. Then I showed you some basic querying on how we can actually add vertices to our graphs by running some simple Gremlin queries, adding some edges and that represented the relationship between our vertices using the Gremlin command line, Gremlin syntax, and then finished off by running some very, very simple queries, right from showing very basic relationships through to showing you how to retrieve vertices with certain properties, right through into more powerful queries such as showing projections and being able to show being able to show you how to find related edges and vertices using more powerful graph traversal queries. And that finishes up our demo. If you want to learn more, I've added some links here to some great learning material and extra resources for more deep dive information on building graph databases with Azure Cosmos DB. Now, a great starting point is the documentation. It's a fantastic place to start if you're still trying to wrap your head around the basic concepts. But if you want to dive a little bit deeper into the graph databases and the Apache Tinkerpop standard itself, I'd recommend checking out their documentation for more details on the Tinkerpop standard. Microsoft Learn has a course specifically focused on storing and retrieving data in the Graph API, which is a little bit more hands-on. Now, for those of you that don't know, Microsoft Learn is a great website with loads of free learning material for you to get your hands dirty with the tech. So if you're wanting a more hands-on learning experience with the Gremlin API and Azure Cosmos DB, I definitely recommend checking that out. And also, if you're looking for more information on Azure Cosmos DB generally, the Cosmos DB team have a YouTube channel where they post some fantastic content, not just on the Graph API, but across all their APIs. This is delivered by the product team and the engineers who work on Cosmos DB, so I definitely recommend checking that out. Cool. A big thank you to Microsoft for supporting the Data Platform Summit, along with the Data Platform Geeks and SQL Server Geeks community initiatives. And don't forget you can win some amazing prizes. So post your selfie on Twitter with the hashtag DPS2020. Make sure that you give session and conference feedback, and also make sure to visit the sponsors and exhibitors for the Data Platform Summit 2020, and make sure you follow the Data Geeks and Data AI Summit on Twitter as well. And finally, a massive thank you to you all. I know that COVID has been a massive challenge for us all this year. It means that we can't see each other in person and meet each other in person, but I'm so grateful that you've all taken the time today to listen to my session on graph databases with Azure Cosmos DB. I hope you had a lot of fun, and I hope you've learned something as well. If you have any questions or you just want to connect, you can follow me on Twitter at Velida, or you can connect with me on LinkedIn using that link there. Thank you so much for joining me again. I hope you enjoyed this session, and I hope to see you all very soon. Bye for now.